Alright, so we're going to first start by discussing some vocabulary words here. So I'm going to start actually down at the bottom. We're going to talk about heat. Heat is the transfer of thermal energy due to a difference in temperature. So we're switching gears here from talking about mechanics, where work was the change in mechanical energy, to heat, where heat is going to be the change in thermal energy. And this change in thermal energy is going to occur due to a difference in temperature. And this is going to be between two objects or between the object and the environment. And this transfer of thermal energy can occur when the items are in thermal contact. So the objects are in contact so that thermal energy could be exchanged. And they're going to exchange energy until you either separate them some way, or thus bringing them out of thermal contact, or they reach thermal equilibrium. So when they're in thermal equilibrium, the temperatures of the two objects will be the same. Because if the temperatures were different, there would be an exchange of thermal energy. So in thermal equilibrium, because they're not exchanging energy anymore, that tells you the temperature of the objects will be the same. So over the next few sections, we're going to be learning the different laws of thermodynamics. And our first one here is the Zeroth Law of Thermodynamic. If object A and B are separately in thermal equilibrium with a third object C, then A and B are in thermal equilibrium with each other. And this is useful because sometimes we don't want A and B to be in contact with each other. So we can use C as a barrier in order to have AB in thermal equilibrium with C, BB in thermal equilibrium with C, and therefore you can know the temperature of A and B. An example of this would be an old school thermometer. So back in the day when you had mercury thermometers, you obviously don't want to stick mercury underneath your tongue. That's kind of poisonous. So you would stick a thermometer bulb underneath your tongue, and underneath your tongue would be in thermal equilibrium with the thermometer bulb. And that's one of the reasons why you had to wait when you went to the nurse's office. They had to sit there with the thermometer underneath their tongue for a couple of minutes, wait for your tongue to reach thermal equilibrium with the thermometer bulb, and that thermometer bulb in turn would be in thermal equilibrium with the mercury inside of the thermometer. So the mercury never actually had to touch your tongue, and you can use the fact that the mercury expanded due to a change in temperature in order to read off the temperature. So this is a way that you can use the Zeroth Law of Thermodynamics. We're now going to talk about temperature scales. Alright, so in the United States we tend to use Fahrenheit in everyday life. So with Fahrenheit, water freezes at 32 degrees Fahrenheit, and water boils at 212 degrees Fahrenheit. And from my understanding is, and mind you, I found this information on Wikipedia, that brine water freezes at 0 degrees Fahrenheit. So whenever you add salt, so brine is very salty water, it depresses the melting point. So this is why you salt the roads during the winter, is it reduces the melting point or freezing point of water so the water doesn't freeze on the roads and cause ice. And 100 degrees Fahrenheit is about body temperature. So 98.6 to 100 degrees, back when they did this, plus or minus a couple degrees, not a big deal. But this is not scientifically based on anything, really. It's just someone picked some arbitrary points. So next we had the Celsius scale. So this is based on water, and that makes sense because water is something we deal with in multiple phases in our everyday lives. So water freezes at 0 degrees Celsius, and water boils at 100 degrees Celsius. Alright, so let's look at the formulas that you're going to use to convert in between the two. So relationships in this course are never going to make use of Fahrenheit. So if you're given a temperature in Fahrenheit, the first thing you want to do is convert it into Celsius. Alright, so after the Celsius scale came the Kelvin scale, and this one is grounded a little bit more in physics, where they wanted to find the absolute lowest temperature you could ever have and base a scale upon that. And that would be whenever you have zero pressure. Because if you have no pressure, then you should have no temperature, because pressure and temperature are proportional to each other. So what they did was they took a series of gases and they took some data where they varied the temperature of the gas and recorded the pressure. And so they did this. Now, mind you, there's a point where you can only go so far back because as you lower the temperature, eventually it's going to turn into a liquid and then a solid. So, and they only wanted to do this with gases. So they took so many data points backwards, and eventually they had to extrapolate back to the x-axis. And they found that no matter what the trend of the gas was, it always crossed the x-axis at about the same point. And remember, the x-axis is the temperature. So when pressure is 0, the x-axis was about the same, and they define that as 0 degrees, or 0 Kelvin. There's actually no degrees, so 0 Kelvin. And this corresponds in Celsius to negative 273.15 degrees. So this is what we refer to as absolute zero. So 0 degrees Kelvin or negative 273.15 degrees Celsius. So to convert between the two of them, Kelvin equals your Celsius temperature plus 273.15, or if you need to convert back to Celsius, you can subtract off the 273.15. As we progress through this material, we're going to find that there are certain formulas where you could either use Celsius or either use Kelvin, because the degree signs for Celsius and Kelvin are the same. So if you're subtracting two temperatures trying to find a delta T, so final minus initial temperature, as long as you're both in Celsius or both in Kelvin, the change in temperature will be the same. But there are going to be other formulas where we're just plugging in a temperature where you're going to have to be in Kelvin, because that is how the formula was scaled. And I will make sure to note that as I go through this lecture series of which formulas have to be in Celsius, which ones have to be in Kelvin, and then which one you can use either as long as both temperatures are in the same units.